Thank you everyone for joining us for a very special distinguished lecture in ECE today. Our guest is Professor Muriel Medart from MIT. It's just, I guess it's difficult to have someone more accomplished than Muriel. She has won every possible award and she deserves it, obviously. And they have spanned from technical awards such as IEEE Communication Society and Information Theory's Joint Best Paper Award. Also, William R. Bennett Prize in Field of Communication Networking. 2002 IEEE Leon Kirschmeyer Paper Prize Award, and several other conference paper awards that we're not even gonna go over them. She also is a recent winner of the Edwin Howard Armstrong Achievement Award, which is given by the IEEE Communication Society for her pioneering work in the field of network coding, wireless communication, and optical networking. She also has received awards pertaining to her mentorship, such as EECS Graduate Student Association Mentor Award, and has served as a housemaster for 7 years in MIT. In 2007, she was named as a Gilbert's Lecturer by the US National Academy of Engineering, and she won the 2016 IEEE Vehicular Technology James Evans Avant-Garde Award, as well as Aaron Weiner Distinguished Society Award for her service to the IT Society. She has also served as the president of the IT Society in 2012, I believe, and she has been for many years served on the board of Information Theory Society. So it's just a great honor for us to have her here, and Muriel started her career in this department, so it's doubly special to have her here. Thank you all for attending the talk.
Thank you. Thank you for the introduction. Oh, wow. Thank you. Thank you for the kind introduction, Nagar, and thank you for the invitation. It really just feels very special to be back here. I'm very thankful to the University of Illinois, not just for all the wonderful colleagues it's provided me through the years, but also because it really did give me my launching pad for a career. And so all of you students who are here, you're at a good spot. This is a good place to get started. I'm going to give a talk which I hope is going to be of interest to a wide audience. And I'll first of all ask forgiveness for all the people, particularly all the excellent people here in information theory and networking, for whom many of the things that I'm going to talk about are probably too rudimentary. But I figured that in order to try to entertain a large audience, it's always better to have some sort of narrative, in particular maybe a narrative which is a little bit more personal. And so, as I said, it's really a personal account of combining theory and practice, which is, of course, something that UIUC is particularly good and famous for. So, this is going to you students and postdocs that are towards the back. I can see you. You know, you're doing your PhD and you're sort of sitting there finding results and, you know, kind of like negotiating with your advisor on, like, you know, papers and graduation and things like that. And that's basically what I was doing. I was doing information theory for noisy channels. I know that one must never not have the units on an axis, so put your favorite units there. But that's what the ipsis is between theory and practice. And when I graduated, I didn't come here right away. I actually went to Lincoln Lab, and I didn't know if I wanted to work long term in a technical field, but I figured I would at least give it a year or two and see what happened. And I realized that also I wasn't a very good engineer. I don't know if I am now, but I sure as heck wasn't then. And in particular, like I really had lost sort of the visceral feel of engineering, which, you know, I had maybe a little bit more as an undergrad. And so I had several offers coming out of MIT, and I took the only offer that had nothing to do with my PhD. And so I took an offer to work on something which was much more applied around network resilience. And part of the reason for doing that is that the group at Lincoln Lab that was doing that under Vincent Chan was just so good. I mean, they could just make, to quote one of my colleagues, they could make lasers sing. And I really needed to get a little bit more of a feel, particularly from all these fantastic people on the applied side of physics, as to really how do you make a network tick. So I had this kind of life here in information theory, because of course, that was also very dear to me. And then I was working on this network resilience. And it was around that time that I came here. And when I came here, I was sort of straddling. And I remember giving my interview talk, which was something so disjointed. I have no idea how you gave me a job. Thank you for doing so, though. Which was, half information theory for fading channels and half optical networking, which is what I had been working on mostly for the next 2 years. And it's here that I met my late, very good friend and colleague of many of us, Ralph Coder. Students don't know him, but you can see his picture in the corridor CSL. It really did something to me to see his picture. And it was thanks to, and this is another reason why it's wonderful to be at this place, it was really thanks to very sage advice from Bruce Hayek. So, if there's anything to learn from this, is whatever Bruce says, you just do, okay? Just, because he's not going to push you. So you just grab that little, you glean that little pearl of wisdom and you just follow it. And you're set for your career. And he handed us what was a draft paper at the time of Alsford, Litza, and Young on this network coding. And it seemed interesting because it combined information theory, network resilience, but it was hard to understand for us. It was very complicated. Sort of the graph theory seemed a little bit opaque. And we decided with Ralph that we would use the time that we spent over there at Beckman getting coffee, which I'll admit now was a significant amount of time. But we would use that time to try to figure out if there was anything there we could do. So at this point, let me interrupt for a second. And again, I've already apologized for all of you who are in the area, but I know that there are people here from mechanical engineering and other areas of ECE and cognate fields that are not in this area, to just give you, the cartoon version of coding. Okay, so what do? When you say coding, you either think about removing redundancy. So for instance, you're using gzip to send a file, or you introduce redundancy because your network is in some way adding errors, erasures, somehow messing up your transmission. Okay, this source coding is a form of channel code is a second, and it's generally point-to-point. Maybe it's point to several receivers, but there's basically nothing happening in the middle. And if you think of the way transmissions happen nowadays, of course, most of the transmissions are not physically, at least point-to-point. They're over a network. So the question is, how do you do transmission of a network? And how do you combine these two aspects? One, which is the efficiency that comes from the source coding. The other one, which is the reliability, comes from the channel coding. So I want you to keep both of those in mind. And I'm first going to touch on the efficiency, the source coding aspect. And later, in the second half of the talk, I'll touch upon the reliability. Okay, but this is kind of the question. I no longer have a point-to-point system. How do I manage efficiency and reliability over an entire network? Should I do it jointly? Does that even make sense? Is the problem too difficult to tackle, and should I always just be considering point-to-point? Okay, so that's really sort of the framework. Now, when we talk about coding, there's a lot of coding out there, block code, convolutional codes, on the error correction case, what people call modern codes, which are kind of not that Okay, thank you very much. All right, we're back in business. You don't have to listen to me yell. All right, thank you. Basically, these error-correcting codes that I was mentioning for reliability and the codes that we're looking at for efficiency. I was looking for my pointer, but I'll use my organic pointer. So block codes, convolutional codes for efficiency, rateless codes, which basically don't assume that you know much about the point-to-point connection, modern codes. As I said, some of them are not so modern. Low-density parity check codes were actually developed in the 60s, but sort of rediscovered later. Thank you very much. And that's the sort of thing that that the evolution has come along. And then, you know, in the 2000s, basically, when I started here, you have these network codes emerging. Okay, so just to pull this together into sort of a system view of what goes on, you have your data, and the data is going to be represented more efficiently by doing source coding, compression. You're then going to add some redundancy by using channel coding. You're then going to transmit it over a channel, which is going to do something to at least some part of your data. You're going to use the redundancy you put in your channel coding in order to decode your data accurately. And then you're going to do the source decoding to recover the original data. One of the things that's interesting here is something called the separation theorem. And what the separation theorem, there it is. Okay, the separation theorem says is that, you know, from a rate perspective, doing this and this together is not interesting. Okay, which is nice because just from sort of a mental hygiene perspective, it would also be kind of a pain, right? You don't want to have a system where you have to tell your Wi-Fi card whether you're sending an email or you're sending a Halloween picture. You know, that would be too much of a pain. So in any case, that would be a reasonable way of architecting things. But it also is, just from a rate perspective, just from an efficiency perspective, there's something called the separation theorem. And we're going to get back to separation theorems later. So again, that's another thing I want you to keep in your head for later. All right. So there I was, you know, as a brand new faculty member here working with Ralph. And I was looking at these kinds of questions of resilience in optical networks. So what happens in an optical network? You know, this sounds like so simple, like how can you work research in this? But trust me, you can, I have. So, you know, you're going here, something breaks, you go on the other side. Aren't you glad you came to this distinguished lecture today? All right. Some things are a little more complicated. Maybe you know, the outside ring is a primary ring. There's a hole that occurs here because of a failure, so you have to go over the hole and you go on the other side. All right? So it sounds very simple, cartoonish, but you know, that's basically the idea. So the first thing that we did is to see whether you could express this as a code. Could you express rerouting as a code? And the key insight that Ralph and I came up with is that when you look at routing, where each node is basically mapping a single one of its inputs to a single one of its outputs, like you would in a traditional router, which inside has a switch, this is a very special case of coding where you're just using a special matrix. Is basically what you're using is a matrix with 0, 1 coefficients, and in particular, generally, unless you have multicast, really what you're doing is you're just using a matrix there's a permutation matrix. You're just permuting the order. Okay? And so if you were to allow yourself to change this coefficient to something else than 1 to go over a different field size, then maybe there would be interesting things that you could do. So let's look at this little network, and let's look here at the incidence matrix of this network. And let me forget about the diagonal. You can deal with the diagonal in different ways. And here are processes. I'm not telling you how I'm representing those processes. Let's think of right now a one-shot decision system. I have two random variables, x1 and x2. I have random variables z1 and z2, and I want to recover x1 and x2 from the observation of z1 and z2. Everybody happy? Okay? And I'm not giving you anything about capacity or anything. Let's just say each of these edges can carry a variable. What happens is you have an f here, and if I look at, in effect, what's the linear response of this whole network, well, I can stay where I am and not do anything. I can apply this edge incidence matrix. So what you see is I've done is I've replaced the 1, which indicates that E1 is incident upon, say, E3. I've replaced it with just a beta. So E1 is incident upon E3 just means there's a non-zero here. And 1 plus f plus f squared plus etc., which of course is just 1 minus f inverse. And I can write the entire impulse response of my network in this fashion. So I don't have to do something like keep track of the different routes. I'm not really doing anything that is sort of recognizably graph theoretic. I'm simply taking the edge incidence matrix, plugging it into the I minus f inverse, and then from there, I'm just basically summing up the path gains. Okay, so f means that you just went one step through the matrix, f squared means you went 2 steps, et cetera, et cetera. And of course, in this case, there are no cycles. We can deal with cycles. Here, there are no cycles, so the whole thing becomes nilpotent. Eventually, you just fall off the edge of the network. There's no more place to go. Everybody happy with this? It's very simple. Okay? Okay, so we basically were looking at this and saying, well, this is just like an algebraic code. And so this really got us from looking at network resilience into sort of the very algebraic end of network coding, but no longer in the sort of messy, very complicated way where you're trying to design a code for each network and try to combine it with graph theory in ways that are subtle and not generalizable. And in particular, one of the things that allows you to do is it allows you to prove theorems just by using crayons, which should be your first, everybody's favorite way of proving theorems. And let's see what that means. So remember that before I had z's, which I wanted to make, in effect, be invertible so that I could recover the x's. All right, so I have 3 x's here. So that's 1, 2, 3. This is my A matrix of whatever pre-coding I'm doing. I have my network, which is some arbitrary mess, which I'm not describing, but it's I minus f inverse. I don't care how bad it is, okay? And then I have my 3 receivers, and each of these receivers, at these z's, you want to be recovering the x's from. Does that make sense? All right, so this is very simple. All right, so what happens is I take my A matrix, I multiply it by whatever mess this is, and then these different receivers are not talking to each other, so all the white parts here are zeros. So I multiply this by that, and I'm going to have an M matrix, which each of these is 3 by 3. This one, what you're showing in the color is that this one only depends on that. It doesn't depend on the other parts. It's not the same matrix, but it's just showing the dependence, okay? So this came from that, this came from that, this came from that. Each of these has to be invertible so that each of those receivers here can receive, that's to say, invert the z's to get back, to invert the matrix I minus f inverse as seen by that receiver to get back the x's. Is that clear? Okay. I see a lot of nods. This is good, particularly at 4 p.m. on a slightly cloudy day. Okay. So if each of these has to be invertible, it just means that if I look in terms of those betas that I showed you before, it has to be that the polynomials in beta, which correspond to the determinant of the blue, the red, and the yellow, each of those has to be a non-zero polynomial. If it's 0, then I have a problem. So all I need to do is make sure that I choose those betas in such a way that I don't hit a root of the polynomial corresponding to the determinant. That's it. That's all I need to do. Okay? Now, in general, that means that I may not be able to stay with the 0, 1. So remember the initial sort of remark was that if I was doing a permutation matrix, it was all 0, 1s. Now, let me look at your favorite non-zero polynomial, x squared plus x. It's a non-zero polynomial, but if I'm in binary, 0 plus 0 and 1 plus 1 are both 0. That doesn't help me. I have to go up in field size in order to avoid a root. Well, that's exactly what we're going to do here. I may have to go up in field size. So as long as I can go up in field size, if each of these is non-zero, then I should have a choice of betas, which is going to avoid all of the roots in all of those submatrices. Okay. Same thing if I have multiple sources. I can, again, just show things by crayons, just by saying, okay, this matrix here, this blue submatrix here only corresponds to, I don't need this. This blue submatrix here only corresponds to this blue submatrix here. And the fact that I had more than one source doesn't really matter. It doesn't really affect me in my structure. Okay, so you can prove a variety of things. And remember that I mentioned Slepian-Wolf, where you can have different sources which may be dependent, correlated in some way, and even though they're being treated independently, you can be as efficient as if you had cooperation. So it turns out, and this is the only nasty thing I'm going to show you, just because for some of you it's interesting, that this idea of network coding really was source coding. It's just source code. It's just compression over a network. And there's a beautiful paper from the early 70s by Imre Cizar on Slepian-Wolf and error exposure, which is how the probability of error varies if you choose a random code. And I haven't told you what a random code is, but we'll get to it. It all looks exactly like the formula we have, except for these terms. The terms with L, where capital L is the depth of the network. So when I have a point-to-point system, like I showed you earlier on, what's the depth of the network? It just makes me happy. What's the depth? Yes, very good, yes. How many fingers am I holding up? Oh, no, that's right. Okay, 1. And when you have 1, log of L is, of course, 0. So basically, what you have here is an extra dependence just based on this depth. But really what we're finding is this is just a type of source coding. So you can't separate source coding from network coding. It's the same thing. It's the same thing. Okay? It's just source coding over a network. We had been looking at depth 1 networks. We can look at whatever. The other thing that comes out is, remember how I said we have these polynomials, and all I need to do is make sure for this multicast that I don't choose a beta, which is going to be a root of one of the determinants, the red, the blue, the yellow. Okay, how do I do that? Well, one of two things. Either I can be clever, or the preferred approach is a slacker approach. I'm just going to choose it randomly. Now, if I have to choose it randomly, I might run into a root. But you know what? If I have enough choices, the probability that I'll hit a root is going to go down, which is bump up your field size so that I'm choosing out of a larger set, and then the probability that I'll hit a root is going to go down commensurately with the size of the field. And if I'm thinking in terms of bits, you know, I have f sub 2 to the n, it's going up exponentially with the number of bits. So, you know, you add another few bits, and, you know, your probability of error probably hit a root is going to plummet. It's very simple. You know, so this is what people call Schwarzschild, but there are other issues that you can do. And you can, as I said, extend this to the case with a little bit more technical stuff, of course, to the case we have correlated sources. Okay, so at this point, we got very happy. And we said, okay, this is great. You know, I'm sure this will get started. You know, people will put this in networks. This may come as a surprise to you. But when most people in networking see that on the right, it doesn't actually cause the sort of endorphins we had predicted. Okay? So this was going nowhere. So you have two choices. One is you go on and do something else, which maybe would have been, you know, the sensible choice, or you try to do it yourself. And this is the next part of the story. So we try to see it ourselves. Now, I told you about a random code, but I didn't tell you what it was. I tell you I'm going to give you, again, a cartoon description. So suppose that I have some data, maybe a packet in the Internet Protocol, an IP packet. It's bits. I'm going to interpret as a vectors on a finite field. Binary is too small. We saw that, right? X squared plus x, and we have 0 or 1 as a choice. That's not good enough. So something big enough, you know, between a breadbox and something, okay? And all I'm doing is, if I have 4 packets, and I'm describing the packets as being vectors, I'm going to take these packets, and I'm just going to sum them up element-wise, using some coefficient such that by being in a large enough field size, I have some non-trivial choice of coefficients. You know, not just 0, 1, but some bigger numbers, okay? And these coefficients are going to be chosen randomly, independently for each and every combination. I haven't, at this point, you say, well, I did that. Wasn't really compression, Muriel. That's all you did was replace something that looked clean, the blue ones, with something that can be used to recover the original blue ones. I have 4 unknowns, 4 equations, but doesn't particularly look more appealing to anybody in the right mind, okay? But okay, all right, just give it to me for the time being. Let's see what happens. All right. What does this mean in practice? Well, we have many different implementations, but here's one implementation which was done with TCP. So TCP is a transport protocol. It's kind of like the workhorse of most of the internet. And basically, you have a subheader, which is indicating a variety of things, but in particular, where you're going, which is an important thing. If you're a packet, you should know where you're going. You have the base, which is basically what field size you're working. You know, is it 2 to the 4, 2 to the 8? How many packets you're putting together? When did your packets start and end? And then a coding coefficient, which was 7, 2, whatever you saw in the previous slide. Now, this coding coefficient, you don't have to necessarily describe it as a number. Maybe you have a shared seed, whatever. Okay? As my packets go through the network and I'm combining different packets together, what I might do is actually just element-wise, I'm going to be basically modifying these coding coefficients through the network. I'm not going to decode. I'm going to recode. Okay? So this is very different. It's not point-to-point. So remember that picture if you had point-to-point in a network. I'm encoding without decoding in the middle. So what does this do for me? Well, let me look at this little cartoon. I have my 4 packets. I'm transmitting it wirelessly, and for the sake of illustration, let me look at a 50% loss to 3 receivers. So I'm sending to Olgitsa, I'm sending to Venu, I'm sending to Negar, and each of them loses 2 packets. And basically, if I were repeating, I would have to repeat each packet because one of the packets is missing from at least one of my 3 receivers. And instead, I'm just going to send 2 combinations, and those 2 combinations will suffice at each receiver, each of the 3 receivers, in order to allow that receiver to recover the original data. So it's very simple. You're basically halving the number of retransmissions. Okay, let me go into this recoding. If I'm considering the entire network as being an end-to-end code, like say a fountain code or something like that, then suppose that I have 10% losses over a daisy chain of 3 links. I'm going to have to add enough redundancy up front to make up for all of the losses that occur in the network. So up front, I have to put that redundancy. But each of those links only has a 10% loss. So if I put enough redundancy just to make it to the next point where I recode, so that I have just enough degrees of freedom, just enough equations here, and then I add a little bit more redundancy just so I can survive to the next hop. So I have enough equations here that I could decode, okay? But I don't need to decode. And I keep doing that. I never have to add more redundancy than what I need just to survive. So I added just in time. And there you may say, well, but I could have decoded in those intermediate nodes. In this particular case, I could, but suppose I had a richer topology where maybe these intermediate nodes don't ever get enough equations to decode. They just get enough equations so that the receiver can decode, but maybe there's some parallel paths which are necessary, which are involved in transmitting the information, okay? So maybe I have another path down here, okay, and I'm splitting in some way. Then this recoding really becomes crucial. I cannot decode at the intermediate nodes. They don't have enough equations. Remember, the idea is just I had these equations, and I was just, once I got the number of equations corresponding to the number of variables, I was able to decode. And so basically what you're doing here is that now, see if I had n of those, n of these hops, I have 0.9 throughput, so it would be 0.9 to the n throughput, which is going down exponentially in n. If I recode, I have 0.9 no matter how long my daisy chain is. Does that make sense? So this is really a code for the network. It's not a point-to-point code that I'm sort of trying to retrofit in a network. It's really a code meant for the network. So at this point, again, we thought, oh, this is great. People are going to want to put it into protocols. It's getting a little closer, but it's still not there. It's still not there because, you present this to people in networking, they very sensibly say, that's nice, Muriel, but you know what? When a packet is missing, I send some notification, an acknowledgement, or a negative acknowledgement, something saying, I didn't get it. Now, we know that this is not the best thing. Remember the example where we had the 3 receivers. If each of the receivers had simply said, look, I didn't get packet 2, packet 3, whatever it is, we would have resent all the packets, and they would have doubled the number of packets that was sent vis-a-vis what was happening in coding. But if it was point-to-point, that wouldn't be so bad. Right? If it was only point-to-point, well, I was missing 2 packets. You're going to have to send 2 degrees of freedom anyway. So, that seems reasonable enough. OK. So then you have to figure out how to do it. OK, so I showed you the structure of an IP package using TCP with coding. What does this do for me? So I know that you have a great network course here. So you may have seen this. This is the cartoon version of TCP. You're going to say this is not how selective repeat works, for those of you who are in the area, so hold that thought, okay? Here's my sender, which is, just very, very eloquently represented by a line. This is my receiver, and there's time, okay, from top to bottom. All right, so I send a packet. The receiver tells me, is going to tell me whether I got a packet or not. I send another packet and get it. Basically, the way it happens is that we call it acknowledging a packet, but it's not really acknowledging a packet. So ACK stands for acknowledgement. Really what it's doing is it's actually requesting the next packet. So I'm the receiver. You sent me packet 1. I say, well, give me packet 2. You sent me packet 2. I didn't get it. Then I get packet 3. And I go, well, that's not what I wanted. I wanted packet 1. And, we go in this sort of silly dialogue for a bit. And eventually, we realize that this is not going anywhere. This is what people sometimes call triple duplicate ACK. I don't know why, because triple duplicate, it makes it sound like there were 6 of them. It's not really triplicate, there's 4 of that, whatever, okay? So that's what they call it, but you see what's happening. And then what happens is the receiver, having sent enough of these repetitive requests for packet 2, finally gets through to the sender. The sender says, okay, let me, stop transmitting, and let me try to go back, okay? And what happens with selective repeat is that it's a little smarter. You don't go ahead and just, keep saying, it would basically adapt, realize that, it shouldn't be going forward. But generally, you can only keep track of a few missing packets. So if you have a fair number of random, if you have 1 or 2 losses, it's OK. If you have more losses, it loses track. OK. So now if we're going to do the coding, the question is, how do I manage the fact that my underlying protocol is relying on acknowledgments? It's going to send me acknowledgement. Never mind that I don't want them. I could try to say, do a rateless code. It's sending them. That's the whole point. Okay, it's sending them because, that's the way it's controlling the flow. All right, so I'm going to send the sum. It's not really a sum. It's a weighted sum. I'm just not showing you the coefficients, but, we're all big enough. We're all sufficiently mature to figure out that, those coefficients are there. I'm just not showing. Okay, so I'm sending you different sums, different weighted sums. Okay. The receiver now gets a sum. Now, what does it do? So when people are trying to do coding with TCP before, they said, this is what I'm going to do. I'm going to code. And then when I decode, I'm going to acknowledge the packets that I decoded. I'm going to send, I got packet 1, packet 2, once I decode. So I'm going to have no acknowledgments, and then I'm going to have a flurry of acknowledgments. That's not what the protocol wants. The protocol wants a smooth progression. It's called a sliding window, not a jumping like crazy window. Okay? So that was not the point. It's not like nothing, nothing, nothing. Of a sudden, I got a whole bunch of stuff. That's not how it was meant to be. Okay? So the protocol is not happy that way. So how am I going to use the underlying acknowledgement in a way that is compatible with TCP, but also makes sense? Well, this is what I'm going to say. I didn't actually decode packet 1. But I, as a receiver, have received a combination, a linear combination of packets, of which packet 1 is an element. And that is the oldest packet, because we want in order to receive packets. That is the oldest packet I have yet to tell you that I have seen. So when the second combination gets lost, well, I don't know about it. All I see is another combination, which is the third combination. I said, by the way, I saw packet 2. I got a combination which includes packet 2, and packet 2 is the oldest packet I've yet to tell you about. So now, we're not getting stuck on the missing packet. Right? We're not like, oh my gosh, you know, send me packet 2, send me packet 2, send me packet 2. I'm progressing. Okay, I didn't get as many packets as you sent me, but I'm not stuck on the one thing that went wrong. I'm concentrating on the things that went right. So we keep going this way, and eventually, of course, we're going to have to catch up. Okay? And how we catch up? Well, I don't need to catch up right away. It could be much later. It could be soon. It could be later. I get to tune that. Okay? So think of like a band diagonal matrix, and I erased one of the rows in there. So I need to add some more degrees of freedom, you know, because I don't have a sufficient rank to invert the matrix. I don't need to add the rank right there. I can add it later. Okay, so I can catch up later in order to unzip backward. Very counterintuitive. That's not the way we usually do things. Okay? But this now gives me a huge amount of design flexibility. And in particular, it means that I don't have to deal with having explicit notification of losses. Of course, if nothing's getting through, I don't want to keep sending stuff. If nothing's getting through, I'm still going to have long waits with nothing coming back, and I'm going to have a timeout. Okay. So at least I have this sort of possibility not to misbehave if I have true congestion or things are really bad. Okay, so this was more on the theory side. At that point, you go, all right, this is very exciting. Well, maybe if you like this stuff, it's exciting, but at least it's promising. So how do you actually do it? And again, this was something where eventually we just decided, well, let's try it. Let's do it ourselves. And here's one example. This is actually work that's been ongoing since the beginning of 2015, but it's still working on, still ongoing with my colleagues in Auckland, Ulrich Peter and his group, and my colleagues in Denmark, Janus Heide and Peter Wingelmann and other guys. Okay, so there is Funafuti. I did not know it existed. How many people knew there was such a place as Funafuti? You did. Okay, the only guys who got very much in the back. Good for you. I had no idea it existed. However, Edward Cocker, Ulrich's student, went there. Actually, he went to many of these islands and spent a huge amount of time convincing the local sysadmin to allow them access to their closet to stick our stuff in. Which you can imagine, right? Because this is like the only link to the outside. Okay, this is the only link to the outside. So you know, they're very wary about letting you stick anything in there. But he explained to me that, you know, he knows how to deal with people, and he actually had a beer budget. Yeah, I mean, literally, you know, this took a few days of kind of convincing and sharing beers. So. That's where the fun comes from. That's right. That's right. That's right. Well, that's where the losses must be coming from. So anyway, so here you have the packet loss here in a log scale, and those little crosses are packet losses. Here you have the dates, and here you see regular TCP and then TCP with network coding. And what you can see is that when the losses are high, and why are they high? This is a satellite link, okay, over an ISP. And being on one of these small islands, you're not going to get fiber. You're very remote, and you don't have the means or importance to get fiber. It's worse, particularly for geostationary, than being in a boat. Because at least if you're in a ship, like eventually you'll get into like a good place in terms of, you know, the satellite beam. Here you're stuck. Okay, you're not going anywhere. So, and you're not big enough that anybody's going to design this satellite beam around you. So, so you're basically stuck with what you got. If you got bad weather, you have to deal with it. So you can see that there are days here where you basically would have had no service if you had had no network coding, you know. Basically, it'd be like 1 megabit versus 3 megabits. Here, basically at nothing. Here, at least you can hold about 2 megabits. And here, at least you're able to get a little bit through, a bit of file download. At least you have email connectivity, intermittent through the day, but it's better than complete death. Okay. So, so that's been a very exciting ongoing project for these sort of highly challenged environments. Now, how about that recoding that we talked about? So here are some measurements. These are measurements taken out of a large military exercise with a lot of trucks. And there are a lot of other trucks, but basically we concentrated on this one guy who's out here kind of on his own, number 4. He's connected to the rest of the network, but just, again, through one of these daisy chains. So you can see these are the losses. The black and red, the first and second hop are not so bad. The last hop is pretty bad. So if I was going to recode, which node would I recode at? That's right, 3. So I'm going to recode at 3. And basically, these are the experiments that you see. You know, this is with regular TCP. You're getting very little through. Just putting in the coding already gives you a lot of the gain. But putting in the re-encoding almost doubles. More importantly, that doubling, it's not so much that just the doubling, is the amount of time also that you're alive. You have multiple minutes here where you wouldn't have even been able to transmit. So the mustard here is the intermediate recoding. The end-to-end encoding is the green, and the purple is just the TCP. There would be times where, you know, you're basically smoothing things out more. Okay, so because, you know, this is nominally a 1 megabit per second. I'm not necessarily thrilled to have 0.6 versus 0.4, but I'm definitely thrilled to have 0.3, 0.4, or 0.3, 0.35 over nothing. Right? I mean, at least I'm getting something through. So the connectivity, the uptime, really, really increases. Okay. At that point, you know, we had really gone into protocols, and a lot of that is now going more into the tech transfer or commercialization, which I'll get to in the end if I have time. At that time, you remember that you went to grad school, and that you did like this information theory thesis, and you go, okay, you know, I went from the upper left-hand corner down to the right-hand corner. Is there something that can be done with respect to noisy channels and sort of a more information theoretic perspective? You know, is there something that we learned, is something that can be done? And remember what I talked about, the source coding, really the network coding is a form of source coding. And remember that separation theorem between channel coding and source coding that I mentioned, that there was no gain of efficiency, at least from a rate perspective, in doing the two together. So you go back, and also, you know, like you spend some amount of your youth, sort of misspent some amount of your youth doing, you know, coding over noisy channels, and you're thinking, you know, if I could do coding over noisy channels and combine it over networks, motherload, okay? I can, you know, the things I could do for years. So you're trying to see, you know, what kind of gains you could have from this. And turns out the answer is none. So you really did misspend your youth. The answer is none. And the answer is, this is really Ralph Coder's out of the last paper. It was published posthumously. Really credit Michelle for doing the bulk of the work of cleaning that up, but it was joint work among the three of us, Michelle and France. So what do we know? We know from Shannon that if I give you a, let's say, memoryless, so some stochastic relation between the output and the input, symbol by symbol, memoryless, then I can transform it into a link, which is a bit pipe which has no errors. Now you're going to say at this point, what kind of stupid idea would it be to take a link that has no errors and try to model it as a link with errors? You know, that's not going in the direction of progress. Well, it's interesting because if you think of a lot of network information theory, you're often looking at doing soft decisions, doing all sorts of very complicated processes that are not just decoding in the intermediate nodes. Okay? And there's a very rich, vast, sophisticated, ever-growing literature on the area. And this is saying if these links are point-to-point, even though I don't know in general the network coding region, I mean, I was a bit triumphalistic there with the multicast and doing my proofs using, red, yellow, green, blue, red, yellow, blue. It was because, I can't, in general, I can't find for, arbitrary connections what the capacity region is. As a matter of fact, the decidability of that problem is still unknown. We don't even know how hard it is. Okay, so it's just really like a basket case of complexity. But whatever it is, it's the same. It's the same between any old memoryless channel and that. Which means that there is no gain to be had from doing a joint channel coding and network coding. Just like there's a separation between channel coding and source coding, and just like network coding is a generalization of source coding, there is a separation there. There's nothing to be gained. Maybe from a complexity point of view, maybe from a delay point of view there is, but just from a capacity point of view, there is nothing to be gained. So all these sort of cross-layer things for the birds, at least from an information theory point of view, for the birds, okay? So this was very surprising. But it definitely told us that, you had to look at the separation. It's a little different if, you have more complicated channels, maybe like wireless channels where you're sharing the spectrum and so on, but not, there are a lot of bounds that you can have. Okay. So at this point you say, all right, from a perspective of just having throughput or just having a capacity region, I don't want to do these things jointly. On the other hand, does this mean that I want to take care of all errors at the physical layer, at the p, y given x level, and only have error-free bit pipes? That's a good question. Well, there are other things that happen. I mentioned complexity, energy. Well, let's look at low-power sensors, okay? If anything is going to show up in terms of complexity or difficulty or having to really economize my resources, then low-power sensors are definitely the poster child for having to be economical in resources. And here's the idea. So this is actually the first chip that implemented network coding. And I want to thank TI for taping out the chip. So we have a very simple error correction at the physical layer, which is just a convolution code that comes with the chip. It's part of the standard. The transmitter is just, again, also very simple in its modulation because that's just what the standard is. And then we're doing the channel coding with the erasure code and network coding over it. So think of a concatenated code. We were having this discussion actually earlier with Maxime about really thinking of the network coding as a concatenated code with an outer code, which is the network code. The inner code was physical layer code. Okay, so here you have, this is the received symbol signal strength. So this is the indicator in dBm, so milliwatts, okay? And so this is in the log scale, and this is also in the log scale. Okay, so uncoded, you can see what you get in terms of packet error rate versus received energy. You can see what happens when you have no physical layer code, just RLNC, physical layer code, no RLNC, and then joint. What I mean by joint, they're actually separate. You're not doing them jointly, but you have both of them going on at the same time. All right. And then you see the signal-to-noise improvement that comes from coding. Because really what coding does is it gives you equivalent signal-to-noise ratio gains. All right. If I do no physical layer code, my physical rate is 1, so I'm adding no redundancy to the physical layer. And I'm using 1/2 code, so basically half of my symbols are just there for redundancy. You can see that if I have a goal of having 10% packet error rate, I get a 1.5 dB. I get a bigger gain if I have a stronger requirement for reliability, a 10 to the minus 2 packet error rate. Now, if I flip it around and I have a rate 1/2 for the physical layer and no network coding, then the gains are different, 2.5, 225. By the way, this is counterintuitive. You would imagine that if I have a stronger requirement, like 10 to the minus 2 versus 10 to the minus 1, as an engineer, you would feel that you would actually prefer to do more at the physical layer rather than leave it to the network layer. Okay, so this is counterintuitive. This really is. To me, to other people, okay? Now, the other thing I want to show you is 1.5 plus 2.5 dB, if you're an engineer, is equal to 3.5. And 3.4 plus 2.2, even if you're not an engineer, is equal to 5.6. Okay? So you're getting cumulative gains. This is in dB, so this is multiplicative in terms of the energy. You don't need to be doing it jointly, but you don't only want to be doing coding at one layer. Okay? Despite issues of separation. So in the last few minutes, I want to talk a little bit about what came next, which I alluded to, which is commercialization. And you see, I'm putting it from theory to practice, because as far as I can tell, it's an amorphous blob. Okay? And I'm sure there'd be people here in the College of Commerce that can tell you how it's actually supposed to work. So again, remember, this is a personal story. It's an amorphous blob. And we were trying to figure out how to put this whole thing together. So what we did is we had patents, including some from here, from Illinois with Ralph. And you have a couple of choices. So just like you had the choice of sort of doing the theory, instead of leaving it there, hoping somebody would pick it up, you can do the patents and maybe even create a pretty patent portfolio, and then hope and pray that somebody will come and license it. The other thing you can do is, and very often tech transfer office or licensing offices will encourage you to do that, is you can find an entrepreneur and line up some venture capital, find a market, and go and put it into a product. The problem is that if you have a fairly polymorphic, sort of versatile type of technology, maybe that's not what you want to do. And actually, if you look at what a lot of companies do right now that have strong IP components, even if they're making products, what they do is they take their IP and they roll it out into a separate, usually LLC type of structure, so they don't leave it with a product. It actually resides outside. Okay, so if that's what people are going to do in the end, the obvious question is, why don't we start with that, right? And then licensing back to different companies that are making different products in different verticals. So that's what we did. But in between, one of the things that you notice is you really need, one of the things you notice is that, again, you can have the algorithms, you can have the IP, you can do the consulting to integrate, but you really need code. And I don't mean code as in an algebraic code. You need code that you can hand to people, which is commercially mature, which has no bugs, which has all the things that you need, and in particular, it's going to work over a variety of different platforms. And what you're trying to do is to get into different systems, whether they be in things such as stadium transmission, vehicle to vehicle, 5G. So we have some, we had demos at the last two World Mobile Congresses with Nokia. So if you really, others are doing transmission of video in planes. I mean, a variety of different verticals, all of which are perfectly sensible, but none of which was necessarily sort of the end-all and be-all of that patent portfolio. Okay, so that's the way we've done it, and I don't know if there's a theory around it or not. So again, this is like a, like I said, it's a personal account, and some of this is also happened very much on the distributed storage side. Okay. So the research sponsors I wanted to thank, and then I'm going to stop there. I just wanted to give, this is my recent research, and these are the blobs that I came up with. So I added a couple more blobs that I'm not talking about. Then I'll take questions. Okay, thank you. Thanks.
Muriel is not only a perfect academician, but you have done great work in startup. I'm glad you put them on. So there is Kodam, Steinwerk, as well as Chocolate Cloud, which sounds the yummiest of them all.
Yes, it is.
So,
thank you.
Any questions for our speaker?
There must be questions, else it was clear as mud. Yes, Shrikant.
So you talked about using TCP. Have you ever tried using it for real-time protocols to Skype or FaceTime or
Yeah. So the question was, did we use it for some real-time protocols? So there's some work right now on putting this into WebRTC, but we haven't tried on any real-time streams of that kind. That is, we as a research group. Some of the startups have, particularly the ones that are doing work in stadia, both for sport, both for kind of football, and also one of them for actually car racing. So they have done that work. It's proprietary, but they have done that work. But I haven't, and my research group hasn't. Yes?
Is this island going to be underwater in 10 years?
That's a very good question. We don't have a solution for that that's based on coding. But you know, I can see the guy with just, you know, his one antenna. Yeah. Maybe they will end up on a boat then at least every so often that they have a, yeah, that's a sad and good question. At least there's a bit of a mountain there. So we did it, by the way, over a variety of different islands. That was just one. But it's over about over half a dozen islands at this point, with very different types of connectivity. Some are connected via GEO, some are connected via LEO, some are connected, so both geostationary and low Earth orbit. Some of them are connected by mix, and they can go from one to the other in terms of beams. Some of the stuff we're trying to do is actually combining the beams also, so that you can get, you know, if neither of them is very good, particularly in bad weather, that's sometimes a combination of the two. And I haven't gone into multipath TCP network coding. That's a very active area of research right now. But yes?
So when you're doing TCP-NC, which is the network code,
Yeah.
TCP, you're recovering from the loss at a later point. So in some sense, you're delaying the congestion control. In certain kind of traffic patterns, could that be a problem because you're not reacting fast enough?
Fast enough, yeah. Yeah. So that's a good question as to, you know, how quickly you're reacting. In a lot of the systems that we were looking at, you had pretty long round trip times. And so you weren't really reacting super fast anyway, you know. But I think that's an interesting question, you know, whether there might be things with applications with very low round trip times.
Especially with content distribution.
Yeah. In many of the cases we're seeing the round trip times are not that low because, again, you're looking at multiple hops. You know, if I have a system where it's just a point-to-point with very low round trip time, as I mentioned briefly, and I'm just doing selective repeat, I can probably get away with not coding, as long as my feedback doesn't have losses. I didn't mention it here, but some of the tests that we did were over base stations. And one of the things that we found was that the good put that we were getting was way, way below the throughput. And there were several reasons for that, but one of them was that the acknowledgements were often getting lost. And so there was a lot of retransmission that was occurring because of lost acknowledgements. And the channel for the acknowledgements, you know, was more unreliable than the channel for the forward. Okay? If you really have error-free acknowledgements, and you have very low round-trip time, and you have selective repeat, then I can get to capacity by just doing repeats. But you have to have all of those things go at the same time. Did I answer your question? Yep. Yeah. Any other questions? Okay. All right. Thank you.